Alright, so in this video we're looking at the Fibonacci sequence from a base 12 perspective, or a base 12 point of view. So I've written the base 10 version of the Fibonacci sequence there. What I've done is the first 24 or 25 or so numbers in the sequence. I think we're all familiar with the sequence where we're adding the previous number to get the next number. So 1 plus 0 is 1, 1 and 1 is 2, 2 and 1 is 3, etc. So I've done exactly the same thing here. I've written the sequence in base 12, so it looks the same, but then as we get past 8, 8 and 5 in base 12 is 1 do 1. So 12 plus 1 is 13, 12 plus 9 is 21, 12 plus 4 is 48, 12 times 4 is 48, plus 7, 55, and so on. So we're just rearranging the numbers, writing them differently. We know it's the same amount. And what happens when we do that is a pattern emerges where we get 0, 1, 0, 1, 0, 2, 0, 3. We go all the way along here until, well, at 12 we get this 1, 0, 0. Looks like 100, but it's actually one gross in base 12. That's the equivalent of 144. So we know that's 12 12s. So that makes sense. In base 12 we see it as 1, 0, 0. Then we continue along and we get to a point where we have a 0, 1, then a 0, 0. So here it's 2 grow, 2 do, x, 0, 0. And then we have a 0, 1 again. And what happens, I haven't shown it here, but this whole pattern of 0, 1, 0, 1, 0, 2, 0, 3 repeats. So there's a 24 iterations of the pattern, and then the last two numbers repeat again. So we have larger numbers, 3, 7, 5, 0, 1, and then it continues. So the numbers get larger, but the last two numbers of every individual number repeats. There's a whole repeating pattern there. So then what I've done is I just put a decimal place there to create 0.01 to get the decimal version. So just to remind you that decimal version is not the same in base 10 as it is in base 12. And we can see that here, 1.00, that's the length of 1. That does not equal 1.44. So 144 does equal 1 gross, but 1.44 does not equal 1.0. So you can sort of realize that 1/10 and 1/12 are different lengths. Got this. The length of 1 is the same, but in base 12, our decimal places are shorter. So 0.3 in base 10 is different in base 12. So just to remind you of that, it's very important to be aware that the real difference lies in the decimal place. And that's where the structure of things emerges, into whole numbers. So we have the length of 1. So that's one aspect that's different in base 10 than in base 12, or base 12 than in base 10. So what I've done next is I decided to multiply everything by 0.75 in this column here, just taking the number previous to the 1, and just to see what would happen. And so what happens is this. 1 times 0.75 is 0.75. 1.75 times 0.75 is 1.0001. So we get the number previous, but then there's a 0.1 at the end. So here, 2.75 times 0.75, we get the number previous, and then 0, 1 again. So we have this extra pattern emergency, 1, 1, 2, 3, 5. We have the entire Fibonacci sequence emerging again, tagging on to the entire, this pattern here is the original pattern, but just one back, and then we get the new version, and up here we have the same thing happening but in reverse. So here we have 0.75 squared, get 0.4701. So there's the 47. Now we have this pattern here, O1, L do L, O2, L do 9, right here. And actually I wanted to point this out also. When we're adding the numbers on either side, here we have the same number, 0.75, then here we have 0.75 and 0.47. So when we add these two together, we get the length of 1. And when we add, then we have the two that are the same, then this one, x3 or dec3 and 1.9, we add those together, we get the length of 1. So there's all of these, every second one going in both directions, adding them together gives us the length of 1. And then in between we have the same ending. So here we get L do L and 0.01, and then here's 0.01 and 0.1 1.147, I have 4 7. So there's a lot of repeating numbers within the pattern that we don't really see again in base 10. So here we have the opposite happening, but the same thing. Here we have O1, Aldo L, O2. So O1, Aldo L, O2, this pattern going this way. Here it's going this way. The Fibonacci sequence going this way. So it's sort of flipped over. And again, we have this quality of being able to add numbers on either side of the 1 to give us the length of 1. Or we have, like here we have 4, L, and then 4. But we wanted to go to 0.5, so when we add this to the 8 here, then we're getting the number. So it's sort of dividing up even more, and then adding reciprocal numbers on either side of the 1, we start to get back to this pattern. So there's just a lot going on here that isn't really visible in base 10. So I just did the same thing again here. Here I'm multiplying by 1.75, so I just multiplying by the other side of the number 1. And we have the same thing happening. 1.75 squared gives us 2 points. So now we're getting the next number in the sequence. And again, with an O1, O1, O2. So again, the sequence is repeating. The Fibonacci sequence is repeating. And we're getting just simply the next number in the series when we multiply. We start off by squaring, and then we get the next number. So here I do it again with 2.75. So 2.75 squared gives us 6.x3, which is 6.dec3, which is the next number here with the O1, and then again we're getting this pattern of the Fibonacci sequence showing up again, and then the reciprocal numbers up here. So there's something happening here. By the time we get to the 4.2 dec, when we square that, then the Fibonacci pattern is showing up, but it starts off with O2, 2, 2, 4. 4 and 2 is 6, 6 and 4 is dec, and so on. So we get, again, the Fibonacci sequence is repeating again. And in a way, it seems like that makes sense when we're multiplying the sequence by the same, all by the same number, that it shows up again. It makes sense in a way, but it doesn't show up that way in base 10. So it's like the pattern comes into a clearer focus or more, yeah, I think that's a good example, clearer focus. The definition of the numbers, the relationships within the pattern become easier to see in base 12. So I just wanted to share that. I've spent a lot of time writing all this on the blackboard. I wanted to show it to you before I erase it all and get on to other examples of how in base 12 patterns emerge that show us that there's a 12ness to the patterns that we are familiar with. In a Fibonacci sequence, we're going to look at prime numbers next, that these patterns have 12 built in, or that, yeah, they're built in base 12, but because we're in base 10, we don't really appreciate it. We can kind of see it, go, oh yeah, there's a 12ness to this, but not really clearly. So I'm promoting the idea that we need to look at base 12 and go deeper into this. So for those of you who love math, there's a lot here to explore. And what's really interesting, or what needs to be explored, is how this relates to actual geometry. We know that the Fibonacci sequence is the math of the spiral. So when we start in the decimal size, or in the decimal version of this pattern, we're going to be creating a spiral that is slightly different dimensions. These are smaller, so that 0.01 is going to be a smaller beginning to the spiral than if we were to start in, doing the same decimal version in base 10. Okay, so if you thought that was information, you can follow me. I'm going to keep exploring, showing you a lot of examples where base 12 brings math into a clearer focus, that the underlying structure of math is 12, and that we're missing a lot by only exploring math in base 10. Okay, so thank you for watching. I'll see you in the next video.